Hi again. Let's take a good look at the scores produced by our doomsday analysis model. You're already familiar with the accuracy score. The accuracy score is just one score you can use to evaluate your model. It's not the only score to consider when deciding if your model is worth using or not. In addition to the accuracy score, Symon provides 4 other scores for a classifier analysis: precision, recall, F1, and area under ROC curve. In this lesson, you'll learn more about each of these scores. Here's a diagram showing our 2 classes or categories: doomsday event and no doomsday event. The red line represents your model and how it divided the incidents into the 2 classes. Yes or no indicates what actually happened. Yes means there really was a doomsday event, and no means there wasn't one at all. So if the model was perfect, all of the yeses would be on the doomsday event side, and all of the nos would be on the no doomsday event side. Accuracy measures how many predictions your model got correct out of all the predictions. In this case, the accuracy is 70% because 7 predictions were correct out of 10. So, for the doomsday event, Captain Verisant had 2 false alarms, and in one case he was really scrambling to save us. Don't worry, it's superhero world, so we're always saved. The formula for accuracy looks like this. Formulas are represented using the terms true positive, true negative, false negative. Positive refers to the positive class or category. In this case, it's the doomsday event category. Negative refers to the negative class or category. In this case, it's the no doomsday event category. True indicates if the model was correct in its prediction, and false indicates if it was not correct in its prediction. Precision looks only at the positive class predictions, or in this case, the doomsday event prediction. It measures how many of the positive class or doomsday predictions were correct out of all the doomsday events predicted. In this situation, the model got 3 correct out of 5, giving a score of 60%. So Captain Verisant was able to stop 3 doomsday events and had 2 false alarms. The formula for precision looks like this. It looks at how many true positives there are out of all the predictions for the positive class. Recall looks at all the actual doomsday events that occurred. In this case, the model got 3 correct out of 4, giving a score of 75%. So Captain Verisant was able to stop 3 doomsday events and was scrambling to save us from 1 event. The formula for recall looks like this. It looks at how many true positives there are out of all the actual positives or doomsday events that occurred. Now there's a trade-off between precision and recall. Let's say we want to make precision even better. Let's adjust our model. Remember that precision is only interested in the positive class. Now we have 2 predictions correct out of 2 in the positive class, giving a precision of 100%. But what happened to our recall? Now we have 2 correct predictions for a doomsday event out of 4 events that actually occurred, giving a recall of only 50%. So, while precision is increased, recall is dropped. Let's adjust the model again to increase recall. Now we have 4 actual doomsday events, and the model classified them all correctly as doomsday events, so our recall is 100%. But what happened to precision? Now there's only 4 correct out of 8 observations, so precision is only 50%. This is where the F score comes in. It determines the trade-off between precision and recall. It provides a way to combine both precision and recall into a single score that captures both properties. To do that, a special type of average called the harmonic mean is calculated. The formula looks like this. There are situations where you would want both good precision and recall. For example, you wouldn't want to determine someone has heart disease and perform an unnecessary surgery if they don't have it. That would be poor precision. On the other hand, it would be equally undesirable to miss finding a person has heart disease and they aren't treated at all. That would be poor recall. In the doomsday analysis, Captain Verisant wants to balance false alarms. That's precision with having to scramble to save the planet. That's recall. Now the last score I want to explain to you is called the area under the ROC curve. It tells you how well the model is capable of distinguishing between two classes. For example, how well can the model distinguish between a doomsday event and no doomsday event? ROC stands for Receiver Operating Characteristics and is a graph that shows the true positive rate and the false positive rate. Symon calculates these rates for you. The black line represents the baseline rates. The red and blue lines would be the results of different versions of your model. For example, the red line could be the result of applying a predictor to your data, but the blue line could be the result after adding more data, cleaning and preparing your data, or even using a different predictor algorithm. Now the area under the ROC curve is exactly what it says it is. It's a mathematical formula that calculates the area under the curve plotted on the graph. The larger the area, the better the model is at distinguishing between a doomsday event and no doomsday event. The area under ROC curve is a great way to summarize the overall diagnostic accuracy of the test. The values are between 0 and 1, with 0 being completely inaccurate and 1 being a perfectly accurate test. A value of 0.7 to 0.8 is acceptable, and a value of 0.8 to 0.9 is considered excellent. Now, before we look at the scores in Symon for our doomsday analysis, I want to explain how the baseline is calculated for a classifier analysis. For each score, there's a baseline score and then the score produced by the model. Recall that the baseline is the simplest way to reach a prediction. For a classifier analysis, the baseline would be the most popular class in the column you want to predict. For example, in a doomsday analysis, the most popular class would be no doomsday or false, because there are more false values than true. So the baseline would assume that there will never be a doomsday event and all predicted values would be false. Your model would be compared to the baseline, and you would be able to determine if it's any better by comparison. Another comparison you can make is to the current process. You know that for Captain Varison, there is no current process to predict doomsday events. He simply randomly patrols the area to see if he's needed. In this demonstration, I'll examine the classification scores in Symon. I'll start by expanding the advanced score section. Let's take a look at the accuracy score. The accuracy score is a score that ranges from 0 to 100%. The closer the score is to 100%, the more accurate the model is. A good or poor score is highly subjective and dependent on the problem you're trying to solve. For example, a score of 60% when predicting human behavior could be considered a good score. But the same score when predicting heart disease would be unacceptable. If your score is close to 100%, you should be suspicious. You could have a column in your dataset that provides Symon with post-event information that you wouldn't normally have. For example, if you're predicting whether a doomsday incident will occur or not, you wouldn't include the historical information about how many people were saved. This is information that would be gathered after the event and should be excluded from the model. Accuracy is calculated as the total number of correct predictions over the total number of predictions. The accuracy score shows that the doomsday analysis model is correct in its predictions about 87% of the time. This score is slightly better than baseline, so you could argue that the model will give Captain Varison an edge in determining where he needs to be and when, especially since you know he has no process in place and is randomly patrolling the area. This would be a good model to use. Let's examine the precision score. It looks at how many in the positive class were correct out of all the positives predicted. The precision score shows that the doomsday analysis model is correct in its predictions for a doomsday event about 73% of the time out of all the doomsday events predicted. Precision is the score to use when minimizing false positives is the focus. In other words, Captain Varison doesn't want a lot of false alarms. This model has a much better precision score in determining true positives than the baseline, which is 0. This is a good model to use if Captain Varison wants fewer false alarms. Let's examine the recall score. Recall looks at how many of the positive class your model flagged out of all the actual positive observations. In other words, how many doomsday scenarios did your model flag out of all the actual doomsday scenarios that occurred? The model gets it right 56% of the time. It's not too bad at preventing Captain Verisant from scrambling at the last minute to save us. Recall is the score to use when minimizing false negatives is the focus. Again, this model has a better score than the baseline and would be good to use. Next is the F-score. It determines the trade-off between precision and recall by calculating the harmonic mean. In this case, the higher precision of 73% combined with the lower recall of 56% gives an okay F1 measure of 61%. This means the model isn't too bad at balancing the times that Captain Verisant has false alarms with the times that he's scrambling at the last minute to save the planet. The score is better than the baseline, so it's better to use this model than doing nothing. The area under ROC curve score tells how well the model can determine whether there will be a doomsday incident or not. It's a great way to summarize the overall diagnostic accuracy of the model. In the doomsday analysis, the value of 86% is an excellent score and much better than the baseline of 50%. And that's it. That was a lot of information about scores. I hope your understanding has improved beyond your baseline knowledge.